So our next speaker is Pietro Vischia from Universidad Oviedo.
Fantastic. Okay, so hello everyone. I'm gonna talk about how to optimize the design of experiments with machine learning for big experiments such as the ones that we have in particle physics. So we have huge accelerator complexes where so this is the Large Hadron Collider. So this ring is 27 kilometers diameter, and we start with hydrogen, and we strip it of its electron, and then we take the proton, we accelerate it in many stages until we reach the largest energies we have achieved as humanity. And we have to control of these orbits. We use a lot of Bayesian methods to control the orbits. We use magnetic fields to bend the trajectory of particles. And then we make these protons collide in 4 points. And one collision looks like this. So we have 2 protons, and there are a lot of physical phenomena that we can model rather well with theory, so mathematically. And in order to detect these complex things, we need huge detectors, such as the ones that Christopher Bishop shown on the first day. So that was Atlas, that is somehow here, and this one where I work is a CMS. So to scale, this is a person, and this is the accelerator. So protons go there, and it's pretty huge. And these things, as I mentioned, we know how to model these phenomena. We have models that are highly stochastic, so we know very well how to sample from these models, but the likelihood is intractable. So if you want to invert them to make inference, you simply cannot. And to give you an idea, each of the randomized choices where you produce a Monte Carlo event results each of the events results in several thousands randomized choices. So this is what one event looks like. And the full chain works like this. So you have like the physics, then we have the data, and to give you an idea, we take data every 40 million times per second, and each of these times we store 100 million readout channels. So this is the size of the things we are talking about. And the simulation we need to match these is obscene. Then, of course, we reconstruct some higher level information. So instead of individual electronics readout, we say there is an electron, there is a proton, and so on and so forth, until we arrive to some typically 1, 2, 3-dimensional summary statistic. And we plug, nowadays we can plug AI basically everywhere across this chain. And the typical inference we do is based on likelihood ratios. And also one thing that maybe is not so common in statistics is that we typically have order of 1,000 nuisance parameters, meaning we have about 1,000 calibration measurements that we need to plug into the likelihood, and we need to profile or marginalize to get the results on the quantity of interests that we are fitting. That typically are a probability of interaction of some particles. And the null hypothesis that we have is the physics that we know. That is this quantum mechanical model that Christopher Bishop also was mentioning. And this is a model that is so precise that we consider it as a real point null hypothesis, even if typically, mostly in statistics, nobody really believes in point null hypothesis. Here we actually have it. And that's also the reason why we typically use frequentist inference. Because as you know, the Jeffreys-Dingeris paradox says that when you actually have a true point null hypothesis, and your alternative hypothesis has a certain wide prior, and when your likelihood has a third scale that is different from the one of the alternative and from the point, of course, then if you use Bayes factors, there is always a certain amount of data that you take that will make you flip the decision with respect to frequentist inference. And in physics, we don't like that. So that's why we typically do not use Bayesian methods for the final inference. What we do is we use histograms that are likelihood-free. So we assume that the actual final likelihood we have is a product of Poisson likelihoods bin per bin with all these nuisance parameters, and we fit that. How experiment design enters this? Well, this is the typical pipeline. We have the physics that gives us the data, the sensor readouts, and the sensor readouts, yes, they will depend on the physics and on the design parameters of the detector. Then typically we go through some higher level features that summarize this data, and in the end we have a low dimensional summary statistic that we use for inference. And these will depend on the construction parameters of the experiment. So traditionally, what we do is we sample some design parameters. We have this simulation and detector simulation chain, and that's the highly non-stochastic, the highly stochastic non-differentiable mess. And then we do inference, we can build a performance metric. And since these simulations are massively complicated, computationally taxing, then in the end, in the past 50 years, we took each subdetector, we used as parameters only something that is really related to individual subdetector, and then maybe the hardware expert said, yeah, there are these 3 or 4 settings that we can try. We sampled those 3 or 4, we find which one is the best, and we use that, completely disregarding all the rest of the phase space. So our idea is to just do that in a systematic way with machine learning, essentially with gradient descent. So if you can build a pipeline where once you have a performance metric, you can let an optimizer change the design parameters in a continuous way, and if you can get the gradient of the whole detector simulation reconstruction chain, then you can backpropagate the gradient and you can have an optimization loop where you find what is the best space. And actually you can do that also using a performance metric that is not anymore a subdetector dependent. You can optimize the whole experiment at the same time. To do that, we have to go back to a Spanish medic, Santiago Ramón y Cajal, which is credited as the father of bodybuilding in Spain. And when he was young, so he got jacked up, and he got in a lot of brawls, street brawls. So he defined himself a camorrista. But he also liked to draw, and a few years later, thanks to the father that forced him to be a medic, he started to draw images of neurons in the brain. And he got the Nobel Prize in 1906 for the connectionist paradigm that is at base of machine learning today. He said the brain works by having these cells that communicate with each other. And if you then study how a cell works, the signals are propagated by a change in the electrical potential in the membrane of the cell. And you can write a differential equation to model this pretty well. Actually, with a neuroscientist, I did for some cells of some species of fish. However, if you want to scale, you cannot nowadays yet solve differential equations for thousands of neurons very fast if the equation is the full one. So in the 50s, people said, okay, let's just approximate this with the linear combination activation function. And this is the machine learning you know today. So you have, this works very well in hardware that is made for matrix multiplication, mainly for gaming. So you have GPUs, FPGAs, you do these matrix products. You still have to solve derivatives because you have to calculate the output, you have a loss function, you have to backpropagate. But still, everything is pretty efficient. So, to calculate the derivatives in computer code, you essentially use what is called automatic differentiation. Because, so if you have a function and you code it, to differentiate it, you can either do it manually, but if you have 300,000 parameters in a model, you cannot. Or you use a symbolic differentiation like a Mathematica, but this results in large expressions, typically even if things improved in recent software. And when you have to do that in a chain, like when you have to do that using the chain rule in sequence, then this becomes too taxing to compute. Numerical differentiation has a lot of issues, as you know. So basically, truncation and rounding errors, if you want to have precise derivatives. And then automatic differentiation is this paradigm that powers everything nowadays. So it's based on the concept of that each equation can be decomposed into atomic operations. This is called a Wenger list, into atomic operations with a known derivative, with a derivative that is known analytically. So if you decompose this equation into a sequence of intermediate variables that represent all the various steps, then at each point you can just store the numerical value of the intermediate operation until you arrive at the end. Then if you want to differentiate with respect to an input, say x0, you can just do that by calculating the derivative of each of these small steps. And since by construction each line depends only on quantities that are above, you can do that simultaneously and get the function and the derivative with respect to one variable at the same time. However, if your model have 200 input variables, then you have to, then the computational cost is 1 column plus 300 columns to get all the derivatives. So then you do it differently. You first calculate all the forward values, and then you differentiate with respect to the outputs, because we are, for instance, the typical setting is 300 to 1 or 2. And if you do that, you use the chain rule, and then with only one additional operation, you get all the derivatives with respect to all the input variables. And when you do that, when you use these, you can replace numerical minimization, and in the likelihood fits with 1000 parameters that I was talking about, you can get a dramatic improvement in the computation time, and the gradients are numerically stable, and things are good. Because when you minimize numerically a likelihood with 1000 parameters, you are guaranteed to have a numerical instabilities, and we see that every day, essentially. So now we are integrating this automatic differentiation in this kind of software. But the broad concept is that if you have an automatic differentiation framework like PyTorch or TensorFlow, then you can use this, you can see the deep learning as a new paradigm where if you can automatically differentiate it, then you can optimize it. And then the optimizable parameters don't need to be the weights of a neural network. They can be anything. So you can differentiate any computer system that you can write in a differentiable way. And that's the paradigm of differentiable programming. So there is a lot of work in recent years. I will skim through the things that we are mostly doing for experiment design. So, as I mentioned, you have these massive simulations that are non-differentiable. So, this is a problem, of course, because if you have the inputs, you have this non-differentiable simulator, and you have the outputs, even if you have an objective function, you have no way of going back to the parameters of the model. But if you use this sampled input and parameter to train a simulator surrogate, so typically a neural network that approximates the simulator, then suddenly you can replace the simulator with a surrogate, and then you can have a feedback loop where you can do optimization with this. But of course, the simulator, the surrogate is just an approximation. And the problem is that it works rather well in the bulk of distributions. It tends to not work well in the tails. And unfortunately, the particle physics nowadays is interested in the tails. So the ideal situation would be to take all this huge simulation software, 10 million so-called and make it differentiable. It's a mess. There are some recent work in the last few years that tries to partially make some of the parts of that big integral that I showed you, try to make them differentiable, but it's still a long way to go. But for some portions, this is already doable. So you can get one part of the integral is called a matrix element, so you can get it with gradients. You can get what we call electromagnetic showers. You can get them with gradients and so on and so forth. But it's gonna take a long time. So for the moment, let's assume we have a surrogate or another way of differentiating this, and try to build this optimization loop. The idea is to find the set of parameters that minimizes a loss function that has a component that tells us how well we are solving the problem, so how good is our, from a physics point of view, is the design. How much does it cost, this layout? So we have to parameterize the layout. And then we have, well, the readout and the actual physics. And the idea is that this is a constraint optimization where we can find a trade-off between cost and performance. However, what we want to do is to optimize big experiments like the Large Hadron Collider, I mean the future versions of it. But we are still far from it, so we started simple. We started with muon tomography, that is a setting where you have a small number of parameters and it doesn't take long to calculate. So you have supernovas in the space, they explode, so I mean there are stars that explode, produce protons, protons arrive to the atmosphere, impact with the atmosphere, and they produce particles that are similar to electrons, but they are 200 times more massive. The mass that they have and their lifetime implies that they can, first, they travel until the Earth without any issue through the air, so the muons go to the air. Second, they enter the matter, so we have 1 muon per centimeter square per minute passing through us. So we can think of using that to do tomography. And it turns out that if you put some detectors before and after some material, the deflection angle of the muons is related probabilistically with the atomic number of the material. So you can do some tomography with this. So we built a differentiable pipeline that where we generate muons, we have 4 layered detectors before and after, we generate a lot of randomized volumes, we obtain a prediction for the volume, we calculate how well we are doing it given the parameters of the detector, and then we backpropagate changing the detector parameters to find which are the best ones. Since it's the relationship between angle and atomic number is probabilistic, we have to it's a bit of a mess. We have to basically take batches of muons at the same time, and this induced a few complications in the code. Plus the fact that we have to have everything differentiable. So, but for instance, a detection panel is an object that has a certain efficiency of detection, and when it finishes, the efficiency of detection drops to 0. Suddenly, this is non-differentiable. How do we do that? Well, we use some tricks. During the training, we don't use the actual physical panel, we use a differentiable surrogate, so we basically put a sigmoid on the borders. And at evaluation time, we use the actual realistic discrete thing. It kind of works. Kind of works in the benchmark that we have, which is a furnace filled with molten steel. And the problem is that you have impurities, and if you look from the outside, you see only the impurities, but you want to know how much impurity and how much steel you have inside. And with this optimization method, we have shown that you can optimize the position of and the size of the detectors to get good predictions, better predictions actually, for the fill level of steel in the furnace. So the square error before optimization is larger than the one after the optimization. We extended it to have more constraints on the panels, but conceptually the results are the same. We did that also for what we call neutron tomography, which is a setting where you have a neutron passing through a gas, and this gas is such that when a neutron passes through it, produces photons. You can measure the number of photons on the walls, and you can build the distribution of the photons. And from the center of the distribution, you can infer the position of the neutron, so where the neutron passed here. And then you have 2 parameters, basically. The pressure of the gas, that tells you that you would have more photons, but you have to spend more energy to keep it. And then you have the collimators, so walls that tell each individual element that they have to look to a smaller portion of the solid angle. And this tells you, you localize better the light at the price of statistics, or the amount of light that you get. And so you can optimize and have a trade-off between these two parameters. And the amazing thing, well, the cool thing, is that whichever starting point you use for any of the parameters, we always stably converge to the same values for the length and the pressure. And for the length, the even cooler thing is that we obtain exactly the same value that the startup company we used for the data obtained from a huge, costly month scan of all the possible values of the collimator length. So this is just the 3D view, so it is nice. The other thing we do is we optimize end-to-end what we call calorimeters, and I realized that I put the explanation of the calorimeters later. So actually, I will briefly skip this and talk about it if we have time at the end. But broadly, it's an optimization of a multi-layered system where each layer can be made of different materials. Some is cheaper, some is more costly. And the algorithm learns what is the best composition. And the non-differentiable part is sampled every time, reconstructed every time, and then we train a diffusion model to replace it to do just the optimization step. The cool thing about these methods is that they can spot, so they are maximally useful when you have something that is not symmetric. So in 2006, people used the genetic algorithm to find the best antenna design, and they still don't know why this is the best antenna design. Similarly, some colleagues a couple of years ago, last year, optimized the placement of tanks that can detect particles that come from the cosmos over a couple kilometers. So this is a field of a couple kilometers in South America. And you detect stuff that comes from the sky. And you want to separate stuff that comes from protons and stuff that comes from photons. In principle, there is no geometrical preferred axis for this optimization. But it turns out that if you start from one of these three setups and you optimize, you arrive to the same structure, which is good, again, stable optimization. And then people still didn't figure out why this triangular structure is considered optimal by the algorithm. So the idea is this algorithm will be maximally useful when the human cannot figure out with our own head some hidden symmetries of our data. And this layout is not something a human would have thought of. In the last 5 minutes, I will tell you how we are trying to scale to the scale of LHC, because these models are already quite computer intensive, particularly in terms of memory. So for all these benchmarks, we had to use some tricks and parallelization and so on to make them fit our available resources. If you want to scale to something with 100 million readout channels, then this is another thing. And then we thought that maybe we have to encode information in a different way. So instead of having those simplified neurons then work with matrices, maybe we have to go back to the neurons like Ramon and Cajal style. Those neurons were richer structures where you have, if you give a current that changes the potential by some value, then you get what we call a spike in the action potential. So the signal is propagated through spikes. Well, this is a realistic, but it turns out that this model actually model pretty well realistic neurons. And if you have a system that works with this kind of neurons, then you can encode any function, for instance, in a non-redundant way. So if you have a function, you can think, I generate a spike signal every time the function increases or decreases by a certain value. What is the advantage of that? That when the function doesn't change much, you don't have to do anything. And not having to do anything in hardware is the most crucial thing. Because the largest energy cost, and therefore also money cost, in chips is when you have to read out something from the memory. So if you have some weights or something that is encoded in the memory and you have to read it, that's bad. With matrix multiplication, you always have to read things, even if the matrix is sparse or mostly zero, you have to read the zero and multiply. With this paradigm, you don't do anything if the problem is sparse. And therefore, you get a massive improvement in energy consumption. And if you use a simplified, so the most simple differential equation that is basically a simple integrator as a model of neuron, then you can, it's called liquid integrated fire model. You can generate these spikes whenever you have some input. You can use surrogate gradients to do a training of this kind of system, and then you can optimize whatever you want. As I mentioned, we have calorimeter. So this is a side view of the CMS detector, and we identify particles in several stages, so from the inner part of the detector to the outer part. We have a few detectors that measure the momentum of charged particles, but let them pass through. And we have others that are called calorimeters that interact with the particle dies there and leaves all their energy. And then you can measure the energy of the particle. And these are called calorimeters. And that's exactly what we will optimize. The calorimeter is basically made of some active material that is plastic, we call it scintillating material, that produces light when a particle leaves its energy. Then we have also some absorber material between scintillating parts to just keep the things within the calorimeter. And for each of the slabs of scintillating material, we have one photomultiplier that reads out the signal. So the resolution of this is driven by the size of the scintillating material. And in the CMS experiment, we just spent 70 million francs to increase the granularity, so to have smaller scintillating elements and a lot of photomultipliers to read out this. Turns out that you can, if you use neuromorphic computing, you can keep the size of the scintillating block, so you don't have to spend money to improve it. And then you can read out the signal with what we light-sensitive nanowires that are sensitive to very small amounts of light. And to cut it short, you can encode these signals into spikes. You can have a full neural network of these, and you can train it to regress the energy that you have and the position of the energy in the calorimeter. And this is massive because it means you don't have to spend a lot of money to increase the resolution. You can just change your readout system. We propose some nanophotonics implementation, and this is the way we think things are going. So if you want to scale up to new experiments, you basically have to drop the digital computing with discrete states that we have. We have to go through neuromorphic processors that have these event-driven computations, and we are looking at quantum computing that offers the benefit that if you can encode it in a quantum circuit, you can differentiate analytically everything. And we have built a group of people, we are about 50 people that where we are doing these things, we are working together, and we are also a bit lobbying the larger coalition for AI in Europe to work at the experiment design and coalesce people interested in these things. Thanks.
So in the interest of time, we will take one question.
Yeah, sorry for that slide.
going back to the tomography problem, do you use like a do you exploit like the GPU primitives or something like, or physical models that are already available for regular tomography, for X-ray tomography, or do you build your own forward?
No, it's our own thing, because here we have we actually track each individual particle. So, for instance, I have one slide in the back. So what we are actually doing is that, so this is the detector. We detect the passage mu for in each panel. We fit a track, and then we match it with a track that is measured outside, and then we individually estimate where the scattering has taken place, assuming there is only one, which is induces a bias, but okay. And then, once we assign this point of closest approach point to a voxel in a voxelized space, then we accumulate a series of muons, we have a distribution of angles, and from that distribution we can infer the material. In X-ray it's completely different.
Yeah, okay.
Thank you very much.
Thank you.